So today we are very glad to have Aldo Bonasera to have a talk. Aldo is a senior research scientist at Cyclotron, Texas A&M University, and also the infant Catania. Aldo received his PhD at the University of Catania in 1980s, and he has worked in many famous institutes like Garnier, Infant, and Jerry. So right now he's working at Infant Catania and also the Texas A&M, the Cyclotron Institute. So his main research interesting in the theoretical nuclear physics, including the nuclear astrophysics with laser, nuclear equation of state, and the nuclear dynamics. So he has published many articles, over 250, and supervised PhD student over 20. So today his talk will be exploring subbarium fusion reaction. And so let's welcome Aldo. So Aldo, thank you. It's your time now. Thank you. Mm-hmm.
Well, thank you very much. And it's really a pleasure for me to be with you, even though it's just virtual. Last time I visited, I guess Shanghai was 2018. A long time, and many things have happened since. But now is a new chapter, so let's start with some new discussion, and very happy to meet old friends, and I hope to make new friends. So I'm gonna talk like Changbo was saying, subbarium fusion reactions. What I mean with this, I will talk about microscopic and macroscopic calculations of nuclear dynamics below the Coulomb barrier. So here I'm showing you an example of an hybrid alpha cluster model, which I will discuss more in detail later, where the system to overcome the Coulomb barrier goes into imaginary time. And then this way we can overcome the barrier, calculate the probability of tunneling, and when it goes to real time, we can see what was the probability of the process to occur. I will show you many of this kind of example using many different models. I started a long time ago with using the Vlasov equation and going into imaginary time, like I did it in the example I'm showing you now. And this came back a little bit and how to say, and under discussion, because many people were presenting many new results. And I'll show you some of those results that were a little bit controversial, some that are still under investigation. So I'm gonna tell you what is this method of imaginary times. First, by showing you the result with the Vlasov equation. And then what we are doing now with one of my PhD students, Theodor Pastas, using the constrained molecular dynamics, which you might be familiar with that, and there's a new hybrid alpha cluster model. Both models, actually, I've been during the years improved. I mean, first I proposed those models, and then I improved and worked with this with many colleagues also from China, including Hua Zheng, that was my PhD students long time ago, and is still collaborating nowadays. And you will see his name in some of the next transparencies. And I will show, when you start a new project or you start a project that has some difficulties, you try to do some simple model. So I showed them a macroscopic model, which is called the NEC model, which I suggested maybe 40 years ago with who was my PhD professor tutor at that time, George Birch at Michigan State. But now we extended that model, which is a simple 2 degrees, 3 degrees of freedom model. into imaginary time to calculate and to have the first feeling about fusion cross-section, and eventually extend this to more involved calculation like super heavy formation and so on. And with another student, Thomas Settlemeyer, we are discussing something that could give us information on the dynamics of subbarrier fusion, and this will be pair production, electron-positron pairs. And this, in my opinion, is a very challenging project, especially experimentally, because it will require some new equipment, and of course, having some good, even underground laboratories nowadays, and having some good detection system. It will be just, I think, very productive to include this and study the reactions that happens to in subbarrier, in this case fusion, but you will see also an alpha decay and fission dynamics. And we plan to extend this also to other fields like laser, where cluster physics, where you produce very strong electric fields and pairs can be produced. And I will conclude my talk with that. So this started a couple of years ago, 2020, during COVID. I guess I will go and visit my friend John Atovitz. And we start discussing about some recent results that had been published on Nature on the carbon-carbon fusion rates at astrophysical rates, so at very low energy. To do that, you have to use an indirect method, a so-called Trojan Horse method, where essentially, if you want to study the fusion of, say, system A, nucleus A with the nucleus X, you prepare a projectile which you call little a. I don't know if you see my mouse, I don't see it. And this projectile is made by some blue particle, which is a spectator, and some red particle, which is the X, the one that you want to study the fusion. So essentially, this happens at relatively larger energy above the Coulomb barrier, but the spectator takes away all the kinetic energy. And the particle X arrives near particle A at the Coulomb barrier. So it already has crossed the Coulomb barrier. And there are techniques to get the fusion cross-section of those two nuclei at very low energy. So this is an indirect method. And when this paper was published, there was a second paper by other authors, notably Akram Zanov, which is also Texas A&M, who criticized this method, saying that in the data analysis, they didn't take into account that the spectator was also a charged particle. So there is some Coulomb effect between the spectator and the fusing system, which should be taken into account. He published this paper soon after. And essentially, if you take it into account, the astrophysical factor, or S star, which is defined here, like you probably all know this, the center of mass energy, the cross-section, times this 87 divided by square root of E, which is the Gamow term. So it's the tunneling through the Coulomb barrier. And then there is some correction, this 0.46 ECM, which is due to the nuclear force. So this is a method to get rid of that strong violent energy dependence of the cross-section by getting rid of the tunneling part. So you expect that this S star will be a smooth number and not changing violently with the energy. And here's the result of, is there a way that I could use a mouse to, no. I don't see my mouse. So I just, so the data up to 2.5 MeV are direct data. And you see the strong oscillation by many different experimental points of different colors, which have been accumulated along the years. And as you can see, going at lower energy, the error bars become bigger and bigger when they are extremely big at the lowest energy, those pink points. The Trojan Horse method gives the full line and is based on this indirect method. And essentially what they do here is to fit their result at high energy to one of the experimental points, and then extend that to the lowest energy. And they saw this bunch of resonances that you can see with this full line, and extend up to 0.6 MeV. In the discussion of Akram and collaborators, they say, no, if you take into account this Coulomb suppression, this resonance will go down up to 4 order of magnitude. And you can see this is a very important question, because such a difference of 3-4 order of magnitude is rarely observed in our field. And the calculation we're giving like the CC, which is a couple channel, we're giving like a constant astrophysical factor, this thick red line. And the other kind like SPP and so on, that time-dependent Hartree-Fock and constrained time-dependent Hartree-Fock, we're giving results that are more or less constant and more or less above 5×10⁻16 MeV per bar. Only one model called the hindrance model at a sharp decay at very low energies, going to about 10⁻14 around 1 MeV, center of mass energy. So this was the situation, and I recall that in the 90s, so we solved the Vlasov equation in imaginary time. How you do that? So you are familiar with the Vlasov equation. It's an equation that solves the mean field and phase space using test particle methods or Gaussians and so on. That you probably are familiar with these things. And this gives you the phase space distribution, which is this F, which is a function of the position of the particles, the momenta, and the time. So you can define a collective variable, capital R in this transparency, and capital P just by integrating over phase space. First, you multiply F by R and integrate over phase space, and you integrate over, say, side A. You divide your system, for instance, if you have carbon on carbon, you divide it into 2 parts through the center of mass, and you call one side A, one side B. So you divide the average position or the average distance on side A and the average position on side B. And their difference is just the relative distance of the center of mass of the two nuclei. And you can do the same for the 2 momenta. So just you multiply by P and integrate on side A minus the side B. If you do that, and then you do the time derivative of this equation, and you use the Vlasov equation, then you get the time derivative of the main part, the relative distance, is equal to P over M. And the time derivative of P is just the gradient of the potential, or the force, if you want, the relative force between the two systems. So this defines the collective variables. Now, when you go in imaginary time, so it means you hit the Coulomb barrier and the 2 nuclei stop. So in order to go into imaginary time, you just change T in delta T or T in I tau, and rewrite the equation of motion. And what you see in the first equation, you get an imaginary momentum. And the second equation, so the derivative of the momentum with respect to T, you just get a minus sign. So the force gets inverted. What does this mean is that your Coulomb force that was repulsive in imaginary time becomes attractive. And of course, you can expect that the nuclear force that is attractive in imaginary time becomes repulsive. So this method was first suggested by Feynman. And we have developed here and in other cases for many body system. And you can play yourself with the simple potential say harmonic oscillator or other potential. Use this method, and you will see that the probability of this process to occur is exactly the same that you will get from quantum mechanics. The great advantage here is that we are dealing with many body systems, so the system can rearrange while it runs into imaginary time. For instance, here's an example still from the paper from '94 of carbon-12 on carbon-12. So at time t equals 0, you prepare your two nuclei. That's the density distribution of the two nuclei. They travel in real time until they get to the point of closest approach, which is about 300 Fermi over C. And there they stop. When they stop there, you change from real time to imaginary time, and they get an acceleration due to Coulomb. So you can see in the drawing already some deformation of the particle being attracted towards each other. And at 600 over C, Fermi over C, they're already approaching, they're traveling inside the Coulomb barrier. Soon after, they stop again because of the strong nuclear force, which is long range and extends beyond the density of the particles. And then you go back to real time. So 700 Fermi over C, you are back on real time. The two nuclei form an egg, and they continue evolving, making a compound nucleus and fusion. So the process occurred of fusion using this technique. And you can see this better if you make a plot of the collective momentum P as function of the collective distance R. So the nuclei in this case will approach from far away, so after beyond 15 Fermi over 15 Fermis, and the momentum becomes 0 around 50 Fermi. This depends, of course, on the energy on the center mass, which is 3.5 MeV in this case. So at this point is when you go to imaginary time. If you don't go to imaginary time, the system will simply bounce back and go back to infinity from where they came from. But if you go to imaginary time, they start to accelerate. And do you see those strange oscillations that appear? This is you can see, if you have a good eye, some deformation also in the picture I showed before. This is due to the rearrangement of the nucleons, of the protons and neutrons, which make those oscillations, and they accelerate towards each other until at some point they hit around about 7 Fermis, the nuclear potential, which now is strongly repulsive. So they hit like a wall, and they stop all of a sudden before an egg is formed. So they stop at point 2. So this is the process of tunneling. And if you calculate the area that is between point 1 and 2, that gives you the action. And the exponent of minus action gives you the total probability for that process to occur. So you understand that this means that the largest is the area, the smaller is the probability. After point 2, you let it go again in real time. And if the system has the right properties to fuse, like in this case, then you see that they start wiggling a little bit around until they make a compound nucleus. For heavier system, the situation is not so easy because they may form a neck. They may form a neck, then they can stop at to point 2. And it might happen that after you take to point 2 and let it go, they bounce back. So that means in that case, there is no fusion. But for light system, and for the system I'm going to show you, the fusion occurs. So you can repeat this process for all the energies. And what you get are the dashed line in this figure. So where the cross section as function of energy in the center of mass is given for the carbon-carbon system. The points are the experimental data that was available in '94. The dashed line is our calculation with the Vlasov equation, and you can see those oscillations, and those oscillations occur into imaginary time. So that means there is some life into imaginary time, and that's something that could be interesting. I will show later some method to explore more what it means to be under the Coulomb barrier. The full line is some macroscopic couple channel model which were available at that time. And of course, at that time, we didn't think that experimentalists could go below 2.5 MeV because, as you can see, the cross section is going down very rapidly. But those indirect methods like Trojan Horse method or other methods came around, and they can go very low energy, almost zero. So we had to do something, and that's what I'm going to discuss you now. But first, let me remind you some of the other results. So this is similar calculation in the paper published, you can see up there, but this time for oxygen on oxygen. And you can see that's the density distribution. On the bottom, you can see the plot of the densities. And the second panel to the right is where they enter imaginary time. And around the third panels, they get to the second point, so they exit imaginary time. And so also for this system, there is a no neck that is formed. And this will be important, the fact that there is no neck formed, because it has to do with this hindrance assumption or discussion that we had before. If you go to very heavier system, not very heavy, but heavier system like nickel or nickel, in this case, the situation is slightly different. That now you can see that some of the imaginary time, the second and the third and the fourth panel, occur while the neck is formed. So there is a different dynamics. Nucleons are transferred towards the neck. There is a dissipation due to this nucleon transfer. There's dissipation due to the. Is there a question, somebody? Some dissipation due to this nucleon transfer. And on the right, you can see the cross section we had calculated at that time for oxygen on oxygen. Again, there you can see some oscillation, but not as much as for the carbon case. And the various reaction with nickel. So nickel 58 on 58, 58 on 64, and 64 on 64. And the agreement was, I would say, reasonable. And essentially, all the parameters, so it means the equation of state and so on that enters the Vlasov equation, they have been fixed in the other reaction, like collective flow or fusion at high above the Coulomb barrier, or the ground state of nuclei and so on. So there were essentially no free parameters for this kind of microscopic calculations. So now if we go back to nowadays, because of the result that we have seen before, and the fact that we had done the calculation up to 2-3 MeV for carbon on carbon, we decided to repeat this and to go to give a new fresh look with different models. One of these is constrained molecular dynamics. Theo De Pastas is working on this. And the model here assumes that you have molecular dynamics. In fact, you have protons and neutrons that are red and blue. And you're making a collision, in this case, of beryllium-8 on beryllium-8, which is something you cannot do in the lab, but probably you can think about doing with some Trojan Horse method or some other methods, which I'm not going to exclude. So we're going to calculate this system as well. And as you can see, the physics is similar to what we discussed before. System enters from imaginary times. Now it's a real time. And so carbon on carbon is on the right-hand side, and it's similar to what you saw before. The major difference, and this is important, is now we have many events plotted on top of each other. With the Vlasov, with the net, we have test particles. For this case, instead, for QMD, we have particles. So if you see, for instance, a red particle that is far away from the other guys, is a particle that is a neutron or a proton that is leaving the system. But this is still a little bit more complicated, and we had lots of complications due to the fact that they have such a strong Fermi motion that you can see here. And so we had a numerical problem and many things to learn. So we decided to go one step down, so an easier model. And we went to a model that is a hybrid alpha cluster model that we had worked out this in collaboration with Zheng some time ago. And in this case, what we do, we treat the system not made as nucleons, protons and neutrons, but as alpha particles. So clearly they have to be nuclei that are multiple of 4, and they have to have even Z and N. And we say, well, these alpha plus particles will act interact to a nuclear potential, which we took as the bus potential, which we had used for the macroscopic model already. So the bus potential calculated for A equal 4. And the Coulomb potential is from just the monopole approximation. This was not enough. It's not enough when the two nuclei, the two alpha particles kind of overlap. At that time, when they overlap, they start seeing the Pauli principle, the Heisenberg uncertainty principle. That means there is a repulsion due to quantum mechanics. And we took this into account by imposing there is a Fermi energy, which we can calculate by assuming that the alpha are have a density distribution. And when the density of the two alpha particles overlap, they produce a fictional kinetic energy, because in effect is a kinetic energy, which goes like the density to the 2/3. So this model has only one parameter essentially, which is the width of this Gaussian. And we can fit that to the carbon binding energy. And once you do that, as you can see, we fit practically all the ground state properties of all the alpha cluster nuclei. So the binding energy is given by the open squares, and the hour values are given by the full circles. The green rhombs or diamonds are just the number of alpha times the binding energy of alpha. So which tells you how much it deviates from this quantity. So from breaking into many alphas. And of course, the larger is the number of the mass number, the larger is the deviation. So we can fit all the nuclei very well apart beryllium 8, which was a little bit overbound. And we did this for a fusion of some examples. If you look at this paper, it was done for studying some toroidal modes that John Hatowitz and his group had proposed experimentally some time ago. In this case, apart studying that kind of feature, we studied also fusion cross-section to see how good the system was. And as you can see, the experimental data given by the black point is rather well described by the model given by the red stars, are relatively high energy. The model fails at low energy near the Coulomb barrier. And the reason for that, you can imagine, is because the part of this reaction are happening below the Coulomb barrier. So now we have a simpler model, the constrained molecular dynamics, which has a clustering embedded in it, which is these alpha particles. And it's relatively easier to deal with numerically, spatially, and we can learn a lot of things from this model. So we decide to extend this model again with my student to imaginary time. So here on the left panel is the total energy as function of time. Total energy, if you are always in real time, should be constant. But when you enter imaginary time, you get this collective force due to the Coulomb and the nuclear force, which does some work. And of course, this means the energy is not conserved when you are into imaginary time. And as you can see, the energy goes up to some point where the nuclear force starts to act and does the opposite work than the Coulomb was doing. And then the system exits at the second turning point, which is around 600 Fermi over C. And the energy at this point goes back to the constant value that we had before, once you take into account the work done by the collective force. And as you can see, the Q value, so the energy above the ground state of the beryllium, of the magnesium 24, is a few hundred keV different from the experimental value. So the model gives a very good description of the dynamics. The times that you can see here, and if you recall the situation with the Vlasov, are roughly the same. This is the same energy of the example I showed you with Vlasov, roughly the same as the times we calculate with Vlasov. The difference is the Vlasov is a mean field, while this is a cluster model. So it's a completely different story. And so there might be some important effect due to clusterization. And there might be, and we saw oscillation in the mean field in the cross section. And now we showed later the oscillation also in the astrophysical factor from the Vlasov equation. And we wanted to see what is the difference if you have a cluster model. So in the right panels on top, you can see a star as function of the energy. And the black points are L equals 0 value, which dominate up to 3 MeV. For L equal 2, they start to be important around 3 MeV. You can see the red points. And then there are all the others up to L equals 6, which give contribution at higher energy. We have put some analytical formula there, but it's not important for our discussion. And below you can see the comparison of our red diamonds or red rhombs to the experimental data, which are the same that I showed before. And also to an AMD calculation, recent AMD calculation, which is given by this brown crosses. The Vlasov equation, the Vlasov result now in terms of a star is given by the green points. You cannot see very well, but you can see the fluctuation that were in the Vlasov equation. And some of those fluctuations are also seen in this hybrid alpha cluster model. The important things that we have to get from this result is that this hindrance that was suggested or discussed by microscopic model or other interpretation of the Trojan Horse method is not seen in this model, nor in AMD, and probably not in Vlasov, even though Vlasov was stopped at 2.5 MeV at that time. So once you do this, you say, well, you know, this model could be very, very useful because you can use for many other things. Some of this might seem a little bit academic. So for instance, this is the collision of a carbon-12 on carbon-12, but now the carbon-12 that is coming from the right is on the excited level of 4.4 MeV, which, as you know, is a 2+ state. In a star, you might have such a situation where the system that is fusing or the system that is making a reaction with other particles in the star, they are in an excited level. So I think it's of some relevance to start to say and study microscopically what happens in those cases. And here you can see that the one to the right that is rotating with this angular momentum of 2+, and is getting closer and closer to the second nucleus. So now I'm going to accelerate a little bit this.
So, and you can see also here that looks like an alpha particle is going away, but the stem cell is dropping back. And so it's at this point, there's a game of resonances. This kind of physics, of course, we cannot study in the lab. I hope, of course, somebody might invent another method. So, but we can study it microscopically with this method or with the post-train molecular dynamics that I had discussed before. So this is a kind of direction that we're trying to pursue in the following months with my student. But again, now we're going back to simpler, as you can see, I'm going from difficult project to less difficult, and now I'm going to a macroscopic project. So this is a model that I worked out with my advisor at the time, Bersch, so 1984, so that's almost 40 years ago. And this model, what we did was a macroscopic model. Macroscopic models are interesting and important when you don't really know what you're doing, and when life might be complicated. So it gives you an idea of what the physics is, which is always important to take into account. So what we were doing there is decide that the two nuclei are just two spheres that colliding towards each other, there is a Coulomb field that pushes them away, and there is a nucleus-nucleus potential. In that case, is the bus potential that tries to bring them together to each other. And this happens until they touch. When they touch, they make a neck. And then there is a strong nuclear force coming by the surface tension, which binds the two nuclei. And the rest is geometry. Just you have to impose volume conservation, and you will get very many different geometries, which will give you the dynamics of fusion, of different elastics, and so on. And when we had, that work was at the beginning is to reproduce time-dependent Hartree-Fock. So here is, for instance, a silicon-on-silicon fusion cross-section with the dashed line as time-dependent Hartree-Fock result, which were obtained at that time. And the full line is our results with this neck model, and gives more or less similar result to time-dependent Hartree-Fock. And as you can see, at low energy, at high energy in zero impact parameter, there was a lack of fusion that at that time was called low L window, which has never been observed experimentally. Essentially, the point there is that when you increase the beam energy, mean field is no more, is not good enough. You need to include two-body collision, or you need to include more viscosity, which will stop the nuclei. Eventually, will go to incomplete fusion or even fragmentation. So, but the model worked very well. We did even for fission, and you can find this in the reference I gave above. So this is an asymmetric fission of California 252. And the full line, in this case, experimental data. There's so much data that it's so precise that are given by full line. Our results were with full points. And these are as function of the mass number for this case. This is a case of deep inelastic, the Wilczynski plot, so-called, where you plot the total kinetic energy of two fragments emerging from the collision as function of the theta, the center of mass. And of course, all the lines, all this are given by the experimental data. And the model is just a full line, which gives all of the range, or if you want, the most probable trajectory in this phase space. Of course, the model is macroscopic, and is you get one for each impact parameter. You get one solution. There are no fluctuations. Fluctuation could be added, but I'm gonna discuss too much about that. And the fusion cross section for this system, which is rather well described. Now you can use this in imaginary time, and that's what we started at the beginning. That's how we restart these things: is to use the neck model to discuss the data that had been published on Nature. So the probability of fusion is given by this expression, which is the usual one, where A is the action, and the action is calculated as the integral between the two regions that we said that the first turning point, the second turning point in the imaginary time. So you see this from this expression that the largest is the A and the smaller is the probability. Now we did something different from the original model, is that we wanted to take into account if there are resonances. So for instance, carbon on carbon, you make a compound nucleus, and if you are at low energy, you might have resonances of magnesium 24. So we modify the bus potential with the Gaussian distribution, where the position, the weights are given by the experimental value of the resonance. So the natural weight, the natural position of the resonance. And an important thing is this depends on the L value. So you need to know the L value, because you do the calculation for different L below the Coulomb barrier. You need to know the position, and you need to know the weight. As you can see, when you have a resonance, what happens is the bus potential increases. So the nuclear force becomes much stronger, and the nuclei stop earlier, which means the action is smaller. So that means the probability to occur is larger, and you get higher cross section. So this is the original result that we got, given by the green line. Now you can see better some of the results. And at very low energy, where the Trojan Horse method was derived, given by the orange point, we get very well reproduction of the position peaks. There is some difference, of course, because experimentally the width of the resonance is large because of the acceptance of the detector that we're using. And there are some other differences depending on the L values. Some L values we didn't think they were supposed to be there. There's L equals 0, L equals 2, L equals 4 to be included. And most of the resonance that we saw here are mostly L equals 0, up to 2.5, where there is an L equal 2 resonance that could be of some value. And the model fits a little bit above the data at large energy, but later on, my collaborator from China, Hua Zheng, and his student, Sunlight Sun is her name, found a little bug, and the green line went a little bit below and fitted much better the data. The Vlasov equation, the Vlasov solution is given here by the red points. And as you can see, the oscillations are very well in agreement with the data, up to 2.5 MeV. So again, in this case, we conclude that the Trojan Horse method gives a good result, and there is no hindrance at very low energies. So we have three different models that seems to give the same results. And here's some of the results now obtained more recently by Xiaoting Sun from Shaanxi University, and she is a student of Hua. And this plot is, the scale has been enlarged a lot to show for the system oxygen plus oxygen, the role of resonance, which is completely different from carbon on carbon. For L equals 0, they got very low energy. The resonance play practically no role. Up to L equals 4. Some resonances are visible, but they are very low, very, very high energy, and their contribution is so small they will not be seen in the experimental data, which is given by the dots. And the Vlasov equation that I showed at the beginning for oxygen is also there with the experimental data, and it fits rather well up to 6 MeV. And this is, if you want, our prediction, waiting that people will do some Trojan Horse method for this system as well. This is another representation of another system, carbon and oxygen. And you can see better here the role of resonance. Without resonance, you get a black line. When you add the giant resonance, the results go a little bit up, and then adding any resonance that are compatible with the L values, you get a better reproduction of the data, even though the oscillations are not seen in this model. A comparison between three different carbon systems, carbon 13 on 13, 12 on 13, and so on, is given this. This is because somebody suggested that carbon 12 on carbon 13 should be the upper limit of carbon 12 on carbon 12. This is true above 3 MeV. Below 3 MeV, because of the Q values and because of the resonance, the carbon 12 on carbon 13 goes below the other case. And for illustration, we also included carbon 13 on carbon 13, which are fermions, and are the only one that shows hindrance. And this is due to the fact that as being fermions, you cannot have all the L values, but just odd values. So L equal 1, 3, and so on. We are now planning to go to a higher, bigger system, like silicon and silicon, again, just to learn how to make some plots, but the work is very good what she's doing. The experimental data is the blue line, and our method fits rather well. And if you go up below at lower energy, you will have a resonance around there. So that would be a good energy to look for a fusion of this system. If the resonance is of the right L value that we have gotten from the, I think it's iron 56. Now I want to tell you something else that could give us more information about the dynamics of subbarrier fusion, about the dynamics below the Coulomb barrier, so imaginary times. And also some information of what happens to the vacuum. We know from relativistic quantum mechanics, the vacuum is not really a vacuum. And if you put strong fields, like strong Coulomb fields, you may excite the vacuum. It means you can produce pairs. You can produce electron-positron pairs, or if the field is very large, muons, and so on. What we are going to do here is do calculation for a subbarrier fusion of light nuclei, but this can be extended anywhere, and I'll show you some extension to other cases. And calculate the probability that a pair is produced and see what effects has on the dynamics. So what we'll do is to invoke the Schwinger mechanism. Many of you maybe have studied this mechanism, for instance, for quark and underquarks. And you said that if you pull a quark and underquark, the vacuum in the middle gets polarized. And since the force is increasing so much, you can produce a new quark underquark pair, which means a new pion. And that's the Schwinger mechanism. But as you know, the linear potential in the case that I was using is nothing else than a solution of the system in one dimension. So if you solve the Coulomb charge in one dimension, you get the linear potential. In 3 dimensions, you get the usual Coulomb potential and some non-relativistic approximation. So we can use this method of first proposed by Schwinger to study the production of pairs when 2 heavy ions collide. There, the main field is given by the Coulomb field. And as you know, the Coulomb field for systems like uranium or uranium can get very strong. So you can produce lots of pairs. And you can have a study on the dynamics of those collisions and also on the vacuum. You start with the Dirac equation. The Dirac equation is very close to the Klein-Gordon equation if you neglect the spin-spin interaction, which is something that we do for electrons since we expect this to be very weak. So you can work this equation by divide by 2mt or m, whatever the mass is. Let's indicate as mt to have a more general. And then you will get something that looks like a Schrödinger equation, but it's still the Klein-Gordon equation. Simply you have done some modification, and you have come out with an effective potential, which is a potential which depends on the distance x of the pair, or the electron-positron pair if you have an electron and positron. And the effective potential is defined here as the transverse mass of the pair minus this quantity, which is the energy of the relative energy of the pair, minus the potential, which could be the Coulomb potential, divide twice the transverse mass. And the transverse mass is defined in this slide. So the idea here is that a particle that is in a negative state can tunnel through this potential, this effective potential of the Dirac sea, many people call it, and emerge as a real particle in a real space. So let's do this more quantitative. So here we have a drawing of our situation, and this is the situation where the probability for this process to occur is the largest. So we have a nucleus of charge Z and another nucleus of charge Z. We assume the same charge for simplicity, but you can generalize, colliding at 0 impact parameter. And they polarize the vacuum. So at the beginning, we assume, for instance, that at the center of those two neurons, so in the center of mass, there is a pair, electron-positron pair, that of course they are in the vacuum, so we don't see it. But now, because of the Coulomb field, the strong Coulomb field, when the nuclei approach each other, they get to some point where there is enough energy that the Coulomb field can create a barrier through which the positron can tunnel through and go in real space and be detected by the suitable detectors. You need to have a good detectors for this, the right detectors. I'll tell you more about this. So this is the dynamic, and some important things are happening. So first, you need to know what is the structure of the vacuum. And second, if the electron is there and is at the center of the two nuclei, now the electron is in between two positively charged states, and so is screening the potential, the Coulomb repulsion of the other nucleus. So that means that effectively, the two nuclei see a lower boundary. In particular, they get accelerated towards each other. So you understand that if you are doing a subbarrier fusion and you produce a positron, then the electron that remains trapped in the middle acts as a screening, but is much screening than what we have discussed in the past due to the electrons that are in the orbits of the nuclei. This is a dynamically created electrons, which screens the two nuclei, which accelerate, and now they can tunnel much more easily. So it might facilitate the fusion process. Let me give you an example how you do this. For instance, we have defined the effective potential, and the potential seen now by a positron. So the positron says the repulsive part, so the V plus on the top. The repulsion, remember, I'm assuming the two nuclei are the same, say carbon on carbon. So the positron is repelled by the two ions, and the Coulomb energy is the one given here. But there is an attraction due to the electron, which is given by E squared divided by X times this Sx, which is a screening factor. So this is where the vacuum enters. Here we have put a screening factor, which we'll assume is the classical value, which means E squared divided by 2mt, which when the particles are on top of each other does not diverge, but it goes to a finite value, which is minus 2mt. The reason for choosing this, you understand that this is the energy that you need to extract the electron and the positron from the vacuum. So to create those two new particles. And the effective potential for the positron is given by this equation where there's the mass divided by 2 minus this term, the energy of the positron minus the V plus. We described above. In this example, I'm going to discuss when the transverse mass is equal to the mass of the electron. And I'm going to do this is just for an example. Assume that at zero, the effective potential is at zero. So that gives you this two solution. One is given by the green line and one given by the red line. And as you can see, if you look at the top panel, the two solutions for x equals 0 do not diverge negatively like you would expect if you didn't have the screening, but starts from a finite value. Now, the two solutions, for instance, the green one, if you look at the potential up on the top panel, it's located at the Coulomb potential, the total V plus shifted up by the mass of the electron. This is already in the continuum. It's already a particle that has been created. So it's not a particle that is from the Schwinger mechanism, but it's to be created by some other mechanism and is unphysical for us. So this is neglected. Instead, the most interesting solution is the one which is red, which of course starts from minus 2 MeV, by 2 MeV. And when it gets to the dashed line around 4 Fermis, that's the point where it hits the Coulomb barrier. So if you look at the bottom panel, the red line, that's where the barrier starts. So now that the particle that is virtual until this moment, it can tunnel through this red barrier and emerge on if you look still at the bottom panel, it emerges around 10 Fermis, 11 Fermis. So at that point, it becomes a real particle. If you go back to the top panel, the particle that was on red at 4 Fermis, it emerged, it goes through the barrier and goes in the long dashed line. So now it's at the V plus the mass of the electron. So that means the particle became real. And of course, in this case, it's a positron for the geometry that we have chosen and for the discussion we have done so far. So that means a positron has been created, and an electron has been left there. So if I go back, all right. If I go to I want to calculate the cross-section for this. The general formula for the cross-section is given by this factor here, where you have the 2L plus 5 plus 1, then you have pi L. This is the probability of tunneling. And this depends on each L1. We are going to look at for L equals 0. So we calculate pi 0. And then you have another term that is PIH, which is the probability that it occurs in a certain time step. Remember, this is a process that occurs in a given time because the two nuclei are dynamical. They're moving towards each other or receding from each other. So the time of collision is, let's say, tau. And let's assume that this time is very small. But in order to be produced, we have to violate Heisenberg principle. We have to violate energy conservation, which means it can occur in a time that is given delta tau, that is given by h bar divided by 2mt. This is the Heisenberg principle. So it means in that time, you can violate energy conservation, have your creation, but you have to take into account that this has finite probability. So the longer is the time, the more probable it is, and so on. Of course, if tau is very long, you have to modify this formula like 1 minus tau divided by delta tau. But if you are interested, this has been published and works by my other student, Thomas Settelmeyer. And you can derive this nice formula like Thomas did, and calculate, for instance, the cross-section at 0 impact parameter. And you get the lines that are given in the top panel for carbon on carbon for different situations. For instance, when the energy, as I told you, the electron makes a screening and the two ions get accelerated towards each other. If the energy of this acceleration of 2Me, you get to the full line, which starts around 3 MeV. And you can understand this, why it starts from there, because you have the mass of the electron and the positron, which is 1 MeV, and 2 MeV comes from to accelerate those ions. So you have to conserve energy. So that's your minimum value. And as you can see, it might get very large. If you want the ions to accelerate at even a larger energy, like 4 or 6, like in the curve, you have to go at much higher energy. But the point here is that the cross-section are not so small that you could measure this positron produced in these reactions. And you can make an experiment where you measure the positron by themselves, the fusion by themselves, and the correlation between the positron and one of the fusion products, so that you make some correlation function to see if there is an enhancement due to this process. Remember one thing, because of the strong field that where the electron is produced, you cannot make the coincidence between the electron and the positron. The electrons get trapped by the two ions. And what happens is that the beginning maybe is pulled by the positron because there is a Coulomb attraction, and they start to try to go up, but then the two ions keep it bounded. And while the two ions go towards each other, this electrons start oscillating, and so they lose completely memory of the correlation they had with the positron. So search experimentally for a correlation will be not correct. You have to look for a correlation, if you want, between the positron or the fusion product that you want to study. And I would expect that there is an increase of the fusion cross-section because of this correct. And now, as I say, you can do this for any strong field. So what about alpha decay or fission? And this is what we did still with Thomas Meyer. Of course, Watson is collaborating with us since a very long time. And on the left panels, you can see fission and alpha decay of californium, 252. As you know, californium is 3% of fission and 97% of alpha decay. So the top panel with the kind of gray line is the alpha decay of californium. It's been multiplied by 97% to distinguish from the fission process. And this is the energy distribution of the positron as a function of the energy minus the rest mass, so the kinetic energy of the positron. As you can see, there is a kind of divergence. This is not due to any particle creation or so on. It's due to the fact that the Coulomb potential goes like 1 over V. And if V is equal to 0 at the time where the alpha emerges from the barrier, then the cross-section diverges. And this is a particular case. And you can see after that, the alpha decays and goes away from the nucleus and follows a Coulomb trajectory. And as you can see, it will produce particles of lower energy. So essentially, you are following the dynamics of the alpha decay. It's not time, but it's proportional to time because it's given by the distance of the alpha particle from the parent nucleus. And this is done for a special case. So we are saying that the kinetic energy of the ions, when the positron is created, is given at the time when the positron is outside the barrier. So the beta equals 0 means that this is the case when the two ions, the alpha or the fission fragments, starts with 0 velocity. But what about if the energy to the ions is given during the tunnel process while the positron is being emitted? In that case, the kinetic energy of the ions is not 0, will be a value different from 0, and you will get lower panel. The peak has disappeared both for the alpha decay and for the fission, as you can see. So this will tell you if there will be good experimental data and if our model makes sense, of course. This will tell us what happens during the dynamics of tunneling. So we are talking of dynamics of imaginary times. If we look more in detail for the fission case, which is different from the alpha decay, fission case might occur when there is a neck between the two fissioning nuclei. And here we can use the neck model, as I described before, that gives good results for fission. And the red line on the scission point, it diverges, is different from the pure Coulomb trajectory, which is given by the blue line. This is because there is a neck which is joining the two fragments, and this is an attractive force against the repulsive force of the two nuclei. So the nuclei gets slowed down. And furthermore, there is a dissipation due to the so-called window formants, one-body dissipation due to the nucleon taking transfer. So that you can see that the dynamics of fission from this, what could be called the saddle point of fission, is completely different from the dynamics of two pure Coulomb charges that are receding from each other. So an experimental verification of this production, again, as function of the energies, which now are much larger, at up to 30 MeV for California, could give us an indication of the dynamics of fission from saddle point to fission, and then from fission to the detector. Not only this, if you want to study heavier nuclei, for instance, on the right panel, you see fission, symmetric fission of some selected nuclei, like thorium to oganesson. You can see that the positron gives you a strong signature if this is the mechanism for the only mechanism for the production of the fission process. And you can distinguish between the fission of every element like oxidation from the fission of thorium, just because the energies of those guys are much higher. And of course, you can always do a coincidence with the fission fragment and study. This is, as I say, it's for a symmetric fission, but you could do this also for asymmetric and so on. So let me conclude. I think I am on time. Yeah, I'm over time, maybe, sorry. So I've discussed here some 3 different models. All the model gives that the S star at 0 energy is larger than 10 to the 16, which means there is no hindrance, at least in this model. So which, together with when you put resonances, it agrees rather well with the Trojan Horse method. We have seen some feature for different impact parameter. And we have seen also that for different systems, those resonances may be not so important because of the large Q value. So we go in a region of excitation energy where maybe giant resonances are more important. We are working for microscopic models, and we obtained already some results which could be very interesting, especially if you start looking on the fusion that may occur in a star, for instance, in carbon stars, where the densities and temperatures are rather high, again, of the order of MeV or so on. And so you might have some nuclei that are already in excited levels. And we have seen that bioproduction can give us some information on fusion and also super heavy nuclei, which is one of the things we're going to explore. And it can be explored to other systems. For instance, the next project for Thomas Settelmeyer will be laser cluster interaction and strong fields that are produced in laser or target interaction. For instance, for TNSA, for people that are familiar with these things, where strong fields are produced and the electron-positron pair may be produced with this mechanism. And we will be working for a super area. We'll try to do calculation for Ganessian or other system if these methods work. Well, I would like to thank you all for your attention.
Thank you. Thank you very much, Aldo.
Thank you.
So yeah, so Aldo gave a very good talk about the NEC model to apply it to carbon and some to get a cross section and the dynamics of the system. So
I see one raised hand.
Xiaodong, please.
Sultan.
Xiaodong,
well, thank you, Aldo. Can you hear me?
Yes, yes.
Excellent. So thank you very much for this very comprehensive talk. Actually, I have been thinking to invite you to give a talk. But you did today before I made it. So thank you very much.
So forget everything and invite me. Don't worry. You can always invite me.
Right. So as experimentalist, I want to ask you some questions. Number one is for the carbon-12 plus carbon-12 fusion reaction, how did you determine the resonance strength for the carbon plus carbon channels? So you have something comparable to the Trojan horse. Can you show the page? Okay. You have your calculation? Yes. Yeah, here. This page. So how did you determine the strength?
So this is a Gaussian, which is normalized to 1. So you just, sorry, it's normalized to, there's some delta E, which comes from the Heisenberg principle. Let me see if I find a better. So the width and the energy is taken from the experimental data.
I'm not saying the resonant width. I'm talking about the partial width for the carbon-12, which determine the resonance strength.
Yes. So there is some. Can you see my screen now?
Yeah, there's a PRC paper. Yeah.
Yes, I have the stupid. Sorry for that. Acrobat doesn't let me read it. I have to open with something else. Of course, this is a phenomenological way, right? Of opening, of calculating this enhancement of the of the potential. I lost. So it's essentially Gaussian. Sigma is the width of the resonance, which is taken from data. Gamma is the energy of the resonance divided by this delta E, and delta E is coming from a characteristic here we take from the model, which is the Coulomb barrier minus the energy of in the center of mass. So this is a pure assumption because it's a macroscopic model, and that's how we determine the strength of this Gaussian, which essentially increases the strength of the potential at very short distances and decreases the action. So
I see.
This is clearly an assumption. It's not coming from any microscopic simulation or so on. When we do the microscopic simulation, our system, but also AMD, I don't know if you noticed my previous, they are still
Kimura calculation.
So I think it's Kimura, yes. They are still semi-classical calculations. So this resonance does not appear in those models. We see some oscillations. And the oscillation, for instance, in the hybrid alpha cluster model are near where the resonances are, but they are not as sharp as in the model. I think if we include some more quantum mechanics there, something in mind, but it's a long story, then this might become a little bit sharper and would be closer to the experimental data, but that's a failure at the moment of the model that we are using, which is semi-classical. So there are some quantum physics, but mostly it's classical. You know, the quantum physics coming from the L that are quantized, but the question of motion, both for us and for AMD, they are practically classical. That is a Pauli principle and so on. I guess you are familiar with it. But it's purely phenomenological.
So my point is, number one, since the Trojan horse use a transfer reaction to obtain this results based on some theory. So the strengths of this S factors depends on their model. So Akram is expert. He write down the formula and has a certain so for example, they depends on penetration factors, depends on the L values. Exactly. And all this informations is still need some more investigations. So did you ever try to use some more like direct measurement data above like a 2.5 MeV up to 6 MeV and try to use those resonance to validate your approach?
Well, you can see the Vlasov, the same figure, this red line is the Vlasov equation. It goes up and down. It's not, and up and down up to the experimental data, which is 2.5. I don't think you can really distinguish. And you can say there is resonances, which are not exactly the same like the data, if you really want to say it. And this will depend on the question of state and the model that you're using. So here, in this region, I'm more confident that there is nothing to fix. That depends on your model. Here, we are talking 1994 for this. So we're using a simple scale potential.
I see. So the red curve is old calculation?
This is a 1994. This is the red curve with the blast of equation 1994, yes.
So new calculation is a green curve, right?
This is with the macroscopic model, and this is the one that includes the resonances.
I see.
Yes.
Yeah, please go ahead.
This fact that is a little bit higher here, I think, as I mentioned, is there was a bug in the code, and which Zhang and his student, Sun, they corrected. Actually, it goes here. So now the new curve goes through the data, and the points are still, the resonance are well fitted. So, but the microscopic, which is the blast of it, fits rather well. And the more recent with the hybrid alpha cluster model, if I can find, I'll show you. And so now here there is another, so if you look at here, there's red points here. These are our result, and there are some resonance here. And I have a better plot, but I didn't show here. I can send you we're preparing a paper where we can see better these resonances as compared to experimental point that here compared to the AMD calculation. And as I said here, I think we will never get sharp resonances because our model is semi-classic. So we have to work on that. But regarding the data, it is true what you are saying, and they call it as a method and not a model. It's a Trojan Horse method and not model. I'm not going to advocate this or that. It's clear that this discrepancy is not a good thing for this method. But they are doing an experiment on carbon-13 to carbon-12, where the neutron is a spectator.
Right.
And the neutron being a spectator means there is no Coulomb in the final channel. So if you're familiar with this method, I'm sure you are. So that means it will put to bed this discrepancy between the two approaches. The point of our work is that our three models, the three models that I've shown, the model by AMD and the other model that I showed before, all this full line here and so on, they never show, all of this model shows this hindrance. So none of these models shows hindrance. And if this will be something that experimental will be proven for this system, means we have to change lots of stuff. Means we do not understand the physics inside the Coulomb body for a microscopic with the methods we have used so far. Yes.
May I take a little more time, Chambo?
Oh, sure. Go ahead.
Aldo,
yes.
I apologize, take a little more time because I'm so interested in your results. So you show this red calculation is your recent calculation. Also have the green curve is earlier calculation.
1994.
No. I talking about you have the H alpha. You just showed H alpha calculation.
Yes.
H alpha C.
Yes.
Right. This green curve compared to early one, the red one, both your calculation, right?
Yes. There's a green point. You can see some point in this thing is not so well. Is this green point and this red points are both my calculation. And now we are doing a third calculation with the constrained molecular dynamics, which is a little bit harder numerical. You saw before because the nucleons are going like crazy.
So what's the difference between the green curve calculation and the red curve calculation you show here? Are they different model or improved model?
Well, they're not improved. I will not call one is a mean field model. So velocity equation, if you want time dependent Hartree-Fock. So this means a nucleon in a mean field. There are no clusters. There are no deuterium or triton or other things that can be formed, like if you do constrained molecular dynamics, or if you do antisymmetrized molecular AMD, which will give all this correlation, which you don't have in Blasov. Remember, this is something we did in 94. At that time, Blasov is the only thing we knew how to solve, actually. And so it's interesting, it gives you those oscillations. And those oscillations, you can read the paper with study, mostly are due to excitation of giant resonances, monopole dipole or low. That depends on the angular momentum. I take away the dipole. So L equals 0 and so on. So those oscillations were coming from that. The new model is we are assuming the carbon is made of alpha particles. So it's already clusterized. Binding energies of the nuclei are very well described, up to mass 200 and something. But they are clusters of alpha particles. And this alpha particle, there is some quantum mechanics, but mostly the dynamics is given by this alpha clustering. And the potential that we are using, alpha potential, is again the bus potential, which we knew worked very well. And that's how the bus did in this time. It fitted some alpha clustering, alpha scattering the nuclei. And as you can see, without fitting any parameter, we get the main curve very well. We see again oscillation, but now the oscillation are different nature. So for instance, we can add the 4.44 level of carbon-12 if one of the two, if we are good to quantize the system, which we have not succeeded yet. Or we could get the oil state, excited level. I showed you one calculation where actually we are making the fusion of the nucleus prepared and the 2+ state of carbon-12 on the ground state of carbon-12. But that's just, we started from there. Otherwise, the levels of this model are still continuous, not sharp.
Very last comment. Can you show the page, the carbon-12, carbon-13, carbon-13, carbon-13 correlation?
This one. So yes.
Yes, this one. So the reason I want you to show this calculation because we observed a very strong correlation between the carbon isotope system. You probably know the papers.
Yes.
So what we observe is carbon-12 resonance, the cross-section is upper bound by carbon-12, carbon-13, and the carbon-13, carbon-13. And I would like to invite you to think about this problem because the current calculation did not show such features. So I think that this is a very nice way to constrain the strength of carbon-12 from very low energy to very high energy. So from probably 2 MeV to 20 MeV. Yes. And this is so I think that this is a very strong constraint, and we tried to explain this problem, this phenomenon, by considering level density. So clearly you have different theory. So I think this will be interesting experimental informations for you and your collaborators to consider.
Right. Well, you know, here I showed only one, but this girl, Shutting Sun, she has done many calculations, in particular where if you look at the astrophysical factor, you see better. And the cross-section, you have to in the order of magnitude, and you don't see the fine detail. So for that, I think we can discuss this this discussion with the following days with Wat Zheng and Shutting, and then we will show you some of the results that we have for those systems in particular. And we can do any other calculation but those systems we have included the resonances, giant resonances, and so on. And we have done quite a detailed study. So it will be interesting to discuss with you further involving those two people, which I don't know if they're following this talk in this moment. But
that's okay. I noticed your collaborators are in China. Besides that, I'm Texas Aggie. I know those people. We can easily find the time to chat. And so if you can have time, we can set up another private meeting to chat. Yeah.
Sure, you can involve them, and if you have some suggestions, you will be happy to do the calculations.
Yeah.
All right.
Okay.
For any other system. Thank you.
Yeah. Thank you, Aldo.
Thank you.
Okay. So another person, Peng Wei Wen from CIAE.
Hello, could you hear me?
Yes.
I have two short questions. First, could you go back to the Gaussian factor used in the bus potential strength? Yeah, left
the
paper.
Gaussian.
You can go to this paper. Yeah, here about. Yeah, this one. I'm wondering, was this adding to the bus potential barrier or the whole distance?
Yes, but it will act only when of course, the energy, when they are very close, the bus potential is still a very short range.
Very short.
So-
So it affects only the potential barrier, you mean?
Yeah, yes, so the bus potential is very short range, so will act only when they get too close to each other. If you saw the distance before, it's around below 8-9 Fermis. For
Okay,
carbon.
another short question is about the turning point. Was it determined by dynamically, or when you know the potential, you define the turning point and set it in the trajectory simulation?
Mhm. That's done self-consistently. It means you run the trajectory. Let me get, for instance, here for Vlasov, but it's the same for all the models. You run the trajectory and you see that the nuclei are starting with their center of mass energy and decreasing their energy while they're approaching each other because of Coulomb. Then at this point, which is, it depends on the Coulomb force and the initial energy, they stop. So when you are at this point, means that the momentum is zero. So at this point, you can go invert the collective force becomes, you go to imaginary time and you follow, and you do the same thing. All this is self-consistent. And then again, the nuclear force, where you see, acts around here. So for the bus potential, this will be much stronger. When you have that modification, it will be like stronger here and will go much faster to zero, let's say, at this point here. And it stops again. That means you are out of the barrier and you are inside the barrier. So the nuclei can fuse. And going back to your previous question, the Gaussian resonance, what it does is decreases this area. It makes it sharper and the area is much smaller, and so the probability is much higher.
Okay,
And I repeat, that's purely phenomenology.
Okay, so it's different for different simulations.
Different energies, different nuclei, it's different, has to be self-consistently done.
Okay, thank you. I have finished.
Okay, thank you. So because of time, so it's a late night for Aldo. I think thank you very much, especially for the stay so late in the night.
Thank you very much.
Thank you. And thank you, everybody. And have a good night or good day. And bye-bye.
Goodbye.
Okay. Bye-bye, Joe.
Bye-bye.
Bye-bye.
Bye-bye, Aldo.
Bye-bye to everybody. Hope to see you soon.
Yeah, goodbye, everybody.
Hi, Joe.
Bye.
Bye-bye.
Ciao, Mehdo.
Bye, Mehran.
Bye.
Recording
And goodbye,
stopped.
Joe.